This is part 8 of the series, Applications of Differentiation. And we're going to continue on with our exploration and practice of the first derivative test. So here, find the relative extrema of this function. And so, as always, our first step, take the first derivative. So f prime of x equals 2 thirds. The inside piece, this is going to be the chain rule, x squared minus 4 to the negative 1/3 power times the derivative of the inside, 2x. And let's do a little simplification here. We have 4x over 3 times x squared minus 4 to the 1/3 power. This is going all the way across. So there's our first derivative. We're looking for where this function is 0 first of all. So we can see when we set it equal to 0, the denominator disappears, because when we set that equal to 0 and multiply by the denominator, it goes away, and 0 equals 4x, so x is going to equal 0. So our first critical number is 0. Next, we know that the critical numbers exist where the first derivative is either 0 or undefined. So we're looking for the values of x that make this denominator 0. And so we have x, let's put it here, x squared minus 4 equals 0, x squared equals 4, x is plus or minus 2. So we have negative 2 and 2 as our critical numbers. Let's go ahead, draw in our line, and put in our anchor values. So minus 2, 0, and 2. Now let's pick test values on either side. So this will be negative 3, this will be negative 1, 1, and 3. And so now we're going to evaluate the first derivative at these test values. So the easiest way to do this is to, if you have the opportunity, is to use your calculator and plug the function in. If you're lucky enough to have a graphing calculator, plug the function in and evaluate using the ask mode if you're using a TI. I'm sure there's another way if you're using a Casio or some other calculator, but evaluate easily. Don't try to do this manually because you'll lose lots of time. So our first derivative at negative 3, or on the interval where negative 3 test value exists, is negative, and in this interval it's positive, in this interval it's negative again, and in this interval it's positive again. So here we have a minimum, here we have a minimum, and here we have a max. So we're going to have a minimum at negative 2, 0, we're going to have a minimum at 2, 0, and we're going to have a max at 0, and that's about 2.5198, and that's a max. Alright, let's do one more example. In this example, we're looking for the relative extrema of this function. So I'm going to rewrite this before we take our derivative, just to simplify it. So f of x equals x to the fourth divided by x squared is x squared, and 1 over x squared is x to the negative 2. And so now we're going to differentiate that. F prime of x is 2x, and this is going to be minus 2 over x cubed. Let's go ahead and rewrite this. So 2x times x to the third is 2x to the fourth minus 2 over x to the third. We will set it equal to 0 and multiply out, and 0 equals 2x to the fourth minus 2, and factor out a 2, so that's 2 times x to the fourth minus 1. This factors to x squared minus 1 and x squared plus 1. This is the difference of two squares. This factors as well to x plus 1 x minus 1. Rewrite that bottom term and the 2, and of course these are all equal to 0. And so our critical numbers at this point are 1 and negative 1 and 1. So let's put our critical numbers here. Don't like that. And so negative 1, 1. And we're going to have a third one, aren't we? Because the first derivative is 0, or is undefined at x equals 0. So we have a critical number at 0. So let's put our anchor values. There's 0, there's negative 1, and 1. Let's make our test value negative 2, negative 0.5, 0.5, and 2. Let's go ahead and evaluate our first derivative at our test values and see what we get. So at negative 2, we are negative. At negative 0.5, we're positive. At 0.5, we're negative again. And at 2, we're positive. So here we have a minimum. Here we have a minimum. But here, because the function, the original function, is undefined at 0, this is actually an asymptote. So we don't have a max or min at this point. So just because we have the indication here, we have to go back and evaluate our function to make sure that these actually are extreme values. So we have a minimum at negative 1, 2, that's a minimum, and another minimum at 1, 2. And that's the first derivative test. Let's move on to the next section. In this section, we're going to be talking about a concept called concavity. And concavity is the concaveness, if you will, of a function. So this function is concave down, this function is concave up. And we're going to be looking at concavity on a particular interval of a graph. We're going to be looking at what the behavior of this graph is between two endpoints. And in general, we're going to be looking at concavity of entire functions and where a function is behaving based on this curvature. Now, let's take a look at the slope of the tangent line at these points. If we look at the tangent line as this thing moves along, you can see that here the tangent line is positive. As we get closer to the top, the tangent line should flatten out. Now what I'd like to do is to show you an example that makes this a little bit more dynamic. So here we have a function and a point on the function, and here is the tangent line to the point. Now between A and B, what we're going to look at is what's happening with the slope of the tangent line as we move from left to right. So as you see, as we move, the tangent line is getting less and less positive. The slope of the tangent line is decreasing to the point where we come up here and it's 0 at the top, and then it decreases. But from A to B, you can see that it's positive and getting less positive, and then negative and getting more negative. So the function, the slope of the tangent line, is decreasing on this interval from A to B. Likewise, if we move in this interval, we reach a point where you can see that the tangent line changes from increasing to decreasing, or decreasing to increasing. So here the slope of the tangent line is decreasing, and now it starts to increase again. So we're going to be looking at those points in particular, but let's look as we go on this concave up part. Notice what's happening. The tangent line is negative but getting less so. The tangent line is approaching 0, and now it's increasing further and getting positive. So you can see that where the function is concave up, the slope of the tangent line is increasing. Slope of the tangent line is increasing. So let's go back and look at that a little bit more formally. So the definition of concavity: let f be differentiable on an open interval. The graph of f is concave up if f prime is increasing. That is, the first derivative is changing positively on the interval, and concave down on the interval if f prime is decreasing on that interval. So that's what we showed in that dynamic graph. Now, to test for concavity, what we're going to be dealing with is, in essence, the rate of change of the rate of change. First derivative is a rate of change, and we're looking at the first derivative either increasing or decreasing. So that's talking about the rate of change of the first derivative. That's going to be the second derivative. So our test for concavity will be, let f be a function whose second derivative exists on an open interval I if f double prime of x is greater, that is, if the second derivative is positive for all x on the interval, then the graph of f is concave up. So over here we said the slope of the tangent line was getting more and more positive, so that means the slope of the tangent line is increasing. So that's what this is talking about. The rate of change of the rate of change, which is what the second derivative is positive on that interval. The function is concave up. And likewise, if the second derivative is negative on an interval, then the graph is concave down. So here, if the rate of change, if the slope of the tangent line is decreasing on an interval, the function is concave downward. So that implies our test involves a second derivative. And what you're going to see is the test for concavity is going to be very closely related to what we did for the first derivative test. Unfortunately, we don't call this test the second derivative test. There's something entirely different reserved for that. But we're going to be doing something very, very similar to that. So let's go ahead and apply this idea to some examples.